So let z be a standard normal random variable and chi-square nu be a chi-square random variable with nu degrees of freedom. Then if z and this chi-square random variable are independent, then this new random variable we say has a t distribution with nu degrees of freedom. Okay? That is, if you take the standard normal and divide it by the square root of this chi-square variable over its degrees of freedom. Okay? We're not squaring chi here. Okay? This is just the symbol for a particular random variable. Okay? Remember, you may want to think of this. This chi-square nu is you can simulate it. It's equal in distribution to the sum of the squared independent normals, independent standard normals. Okay, nu of them. All right. Okay. So, why do we care? Well, so this is just a definition. We're not going to prove this. There's nothing to prove here. We're just saying that this thing behaves. It has this other distribution. Okay, why is this useful? Well, so let's take a look at this. What if I write down what we just wrote down up there? T is this standard normal divided by the square root of this chi-square variable over its degrees of freedom. Okay. Well, I know that this behaves like it's equal in distribution to, remember this z, this standard normal, this is like if I take x bar, my sample mean, minus its mean over sigma over root n, right? All of this stuff behaves like a standard normal, right? And then also, let's see, this all of this stuff down here. There's something that's of practical importance to us that behaves like a chi-square random variable. Remember from that previous theorem there? If we take n minus 1 times the sample variance divided by the actual population variance. So all of this stuff behaves like a chi-square random variable with n minus 1 degrees of freedom, right? So now I'll just divide that by n minus 1. Okay. All right. So I've replaced sort of these more theoretical random variables that with things that are maybe of more practical direct use that behave like them, right? This behaves like this. And this stuff behaves like this. Let's see if this simplifies a little bit. Sure, it does. First of all, this is sigma basically effectively in the denominator, and then this is also a sigma, right? Because I'm taking the square root of sigma squared. In the numerator, basically, those are going to cancel. Also, these will cancel underneath the radical sign, provided n is not equal to 1 exactly. And then what am I left with there? X bar n minus mu over sample variance over root n. So all of this stuff behaves like a t random variable, and this is super important. This is super important in statistics, especially because it turns out you'll never know the population standard deviation, right? Before we had a sigma here where the sample standard deviation is. But if I take a sample and take the sample mean, subtract the population mean, and divide by the random sample standard deviation over the square root of n, this thing behaves like a t random variable, provided I'm sampling from a normal distribution. Okay. And what does a t distribution look like anyway? Well, it looks a lot like a normal. It looks sort of like that. This red curve is a standard normal curve. This one is a T density. Okay. So you can see that the standard normal curve is higher than the T density here around 0, and it's actually lower than the T curve as you get farther out in the tails. Okay, so we say that this T curve has fatter tails. This has a just by looking at the picture, you can tell that it's going to have a larger standard deviation or larger spread to it. Okay, but so this is sort of another way, maybe in a sense a better way to standardize the random sample mean if you're sampling from a normal distribution. Okay, if you're sampling from a normal distribution, we know that this quantity is going to behave like this T distribution here in blue. And by the way, as the sample size goes up, these T curves converge pointwise to the standard normal density. Okay, that is, these, maybe you could say it like this. F sub T with its degrees of freedom or whatever, n minus 1 of x converges as n goes to infinity to the density for a standard normal, okay, for all x. All right. Okay, so let's assume that we're back on this milk job here, and the company you work for claims that the mean amount of milk distributed into each gallon jug is 1 gallon, and that the standard deviation is well, maybe you don't know. Maybe you don't know what the sample standard deviation is, but mean 1 gallon, and they're normal random variables. Okay, so this is the company's claim. Company's claim. Okay, so your job as a quality control engineer is to go in and test this claim, maybe every day or once a week or something like that, maybe several times a day. So, so maybe you go in and you don't want to waste a whole lot of milk. You're going to take a sample of size 7. Okay, and in this sample of size 7, or from this sample of size 7, rather, you find that the sample mean was, say, 1.10 gallons. And you also got a sample standard deviation. Sample standard deviation. And again, what is that? That's it's like the average squared deviation from the sample mean. Okay, it's from 1 to n, but it's not quite just the average. It's you take 1 off the bottom there. It's almost the average, and then also you take the square root of the sample variance, and so that turns out to be, let's say 1.10 gallons. Okay, so your job now is based on, let's say it's 0.018, okay, gallons. Okay, sorry. So your job now is based on this information in your sample that you've taken a sample of size 7. It's coming from a normal distribution, and your sample mean was 1.1 gallons, and the sample standard deviation was this much. Should you refute the company's claim that it's just the machine need adjustment? Well, all this previous stuff about the T distribution remember that this stuff behaves like a t random variable. Let me just write it like this: according to theory, which is true, x bar n minus the actual mean, which I'll take to be this, okay, according to the company, divided by the sample standard deviation over root n, should behave like a t random variable with n minus 1 degrees of freedom. So what I'm going to do then is I'm going to just calculate this, the value of our random variable, and look out under a t-curve and see how strange it is. See, so for our example, when we call this a test statistic, I'll take my the random sample mean minus the mean that the company claims, divide by the sample standard deviation. I'm putting these in lowercase letters, by the way, because they're no longer random variables. Our sample mean was 1.10 gallons, and the mean that the company claims is 1 gallon. And the sample standard deviation that we got, I guess, was 0.018 gallons. I'm going to divide that in the bottom by the square root of 7, right? So 1.1 minus 1 is 0.1, okay? And divide that by 0.018, and then multiply by root 7. 14.6986. See that? 14.6986. So the question now is, if what the company says is true, it turns out that this is the true behavior of that random variable x n bar minus mu over s over root n. Okay, so the idea now is I want to know just how strange is this number. Where is that? It's going to be over here somewhere, I think. Okay, so is that very far away from 0? Okay, if I was looking underneath a standard normal, then the answer would be obviously yes, because I know from experience that 3 or 4 standard deviations out under a standard normal is pretty far. But so this I'm going to know the probability of observing a test statistic this far to the right or more. Okay, that's what this is. Now I can get this by doing, guess what, TCDF with my calculator. Okay, because we're under a t-curve and it's a cumulative distribution function, basically. We're wanting to ask the calculator to integrate for us, and it's there. It's in that distribution menu in your calculator, TCDF. I want my lower endpoint, which in this case is that number, 14.6986. Go up to something really, really high. Okay, that's pretty high. And then finally, I want to put in my degrees of freedom, which is it's 1 less than our sample size, right? 6. Okay, 3.11 times 10 to the negative 6. Oh, so what did I just do there? 14.6986, comma, a bunch of 9s, 9999, 9999. 9, 1 more 9, and then 6 degrees of freedom. That turns out to be roughly 3.11 times 10 to the negative 6, or about 3 parts in a million. That's small. So the chance that you would see something that strange or stranger is extremely small. So probably your machine is out of whack.